Hello, everyone, and welcome to this Data AI Summit presentation, in which we will talk about supercharging your Spark queries using the Spark UI with the SQL tab. So my name is Max Steune. I'm a resident solutions architect at Databricks, and my co-presenter will be Stefan van Wouw, who is a senior resident solutions architect also at Databricks. So what are we going to talk about today? So in the first part of this presentation, we are going to give you an introduction to the Spark SQL tab, which is one of the tabs in the Spark UI that most of you are probably familiar with. Next, Stefan will introduce you to all the most common components that you will find in the query plan, which is, again, the Spark execution query plan within the Spark SQL tab. And finally, I will then walk you through a couple of scenarios, some real-world Spark scenarios in which we can use the knowledge that we gained about this query plan and the Spark SQL tab to optimize your Spark queries to make them really as optimal and as fast as possible. So yeah, as just said, in this first part, I will just give you a brief introduction to this Spark SQL tab. So first of all, why should you really know about the SQL tab? Well, really, it gives us two important pieces of insights, right? So it shows you how exactly the Spark query is executed. So as most of you probably know, when you submit a data frame or a Spark SQL query to Spark, it first goes through this optimization engine called Catalyst before it actually generates this final query plan that gets entered into the JVM. And this SQL tab gives us some insight into this final query plan before it goes into the JVM. And so we can use this SQL tab to really reason about whether this final physical plan is actually the most optimal possible plan that can be executed. So we can then also use this query plan and the SQL tab to really reason about the query execution time. And again, critically think about whether it is the lowest execution time that we could possibly achieve using this query. So how do we actually get to the SQL tab? On the below part of the slide, you will see a screenshot of the Spark UI. So what you simply do is first you, of course, go to the Spark UI within your cluster, and then below there, you can click on the SQL tab that you can see in the little yellow rectangle. When you click on the SQL tab, you will then see a list of all the SQL queries that you have executed within your cluster. And when you then click on one of the descriptions, so on one description that's associated with the SQL query, we then actually get a visual overview of the query plan, which I will show you later on in this presentation. So what exactly is a query plan? So as I already just mentioned, a Spark SQL data frame or dataset query, it will go through this optimization engine called the Spark Catalyst Optimizer before it is finally being executed by the JVM. So actually, the Spark Catalyst Optimizer really executes a series of optimization steps before finally arriving at the final execution plan, which is called the selected physical plan that you can see on the right. And so what we typically mean with query plan is this final selected physical plan, which is the output of the Spark Catalyst Optimizer. So where does this query plan actually sit in the hierarchy? So I think most of you are already aware with this famous hierarchy that goes from Spark job to job stage to Spark tasks. So if we now go from right to left, we know that one Spark stage actually executes a number of tasks. And in your cluster, each executor core can execute one task at a time. But and one Spark job actually, again, executes multiple stages. So maybe you already know this, but one Spark job is usually cut down by what we call shuffle boundaries. And the shuffle boundaries then dictate how many stages you have for one Spark job. The query plan actually sits on top of these Spark jobs. So one Spark query can actually generate multiple Spark jobs. And then on top of that, again, is this data frame action. So that could be something like dataframe.count or dataframe.write to Parquet, which can, again, actually generate one or more queries. So in this slide, I just want to show you a simple example of how this hierarchy actually plays out. So on the top left, we have a very simple Spark query in which we have a data frame that contains some sales data. And what we want to do here is we want to filter on certain item ID codes. And for all these item ID codes, we want to get the total number of sales for each item ID. So this will be a filter query, after which we do a group by, and then we aggregate the sales per item ID. We're then going to trigger the query by doing a write command on this data frame. So this is then the actual data frame action, which is then the first step. So this query will then generate, in this case, one SQL query, which you can see on the top right next to number 2. So that will be the associated SQL query that's associated with this data frame query. In the following slides, we will actually click on this query and see what kind of information we get then. So this query, again, generates one Spark job. So this will then be job 24 that you can see on the top right. And this job will, again, have generated 2 stages that you can see on the bottom right, which are stage 50 and stage 51. Finally, you can see on the bottom left on the summary tab that these 2 stages in total then generate 9 tasks. So what I just want you to pay some attention to is that one way to go to the SQL query is that you simply just go to the job that's associated with this data frame query, and then you can just click on the blue number next to associated SQL query on the top right. So what does this SQL query look like? So we see a visual overview of it on the right, and we see the actual generated physical plan, so that is the query plan, on the bottom. And so we can actually do a simple mapping exercise, right, using this simple query. So on the very top right of the SQL plan, we see what is called an in-memory table scan. And this in-memory table scan actually references the fact that we read this data frame from a cached data frame. So it's actually reading the data frame from in-memory, and that is what in-memory table scan means. Next, we're doing a filter operation, and that is what you can see by following the yellow arrow. So a filter operation using the data frame query actually just leads to a filter operation in this final physical plan. And then we see a bunch of operations that have to do with the aggregation query. So it actually performs 2 hash aggregates, and in which between it is doing a shuffle exchange. And Stefan will explain a bit more on why it's actually doing 2 hash aggregates. For now, it's okay to know that this group by plus aggregation actually leads to these aggregation steps in this final physical plan. The final step of this physical plan is then the actual write step, which is denoted by the overwrite by expression that you can see on the bottom right. So this is really a very simple query, and you can kind of already intuitively see how all these steps in the data frame query map to these physical plan operators that you see on the right and in the physical plan on the bottom. So, but what we now really want to cover in this presentation is what possible operators exist in this physical plan. So we have now seen a filter and a hash aggregate, but what do these actually mean? And what more operators like these do we actually have? And next, we also, of course, have these small details, the details section within this plan that you can see on the right. And the details, they convey all the metrics, all the Spark metrics that are a component of this physical plan. And Stefan and I will also go a bit more into detail in how to use these details to potentially optimize your query more. So finally, once we have all this knowledge, so once we gave you this brief overview of all the operators and all the metrics that you can analyze using this SQL tab, I will then go over a couple of scenarios that uses the above knowledge to optimize some example SQL queries. So with that slide, I just finished the introduction to this presentation, and Stefan will now take you through an overview of all the common components of the physical plan.
Yeah, thank you, Max, for this gentle introduction. So I will actually go over some common components of the physical plan here to kind of give you a breadth view over like what kind of components do exist. So this is quite technical, but I think it's important. So essentially, the source code of the Spark project can bring a lot of information to you, right? So let's first discuss how a physical plan is actually represented in the source code of Spark. So it's actually represented by the Spark plan class in the source code, which both functions as a data structure that can be iterated over and manipulated as like a tree of operators, but as well as it will dictate what properties each of the operators have to adhere to. So to make it a bit more visual, on the left, again, you see an example physical plan as shown in the Spark UI. So here you see different operators. So really, most of the boxes, each of the boxes is basically an operator, right? So you see scans at the top. You see transformations represented, for example, the columnar to row, but also union and override by expression. So if you generalize these, you can basically look on the right that there are certain operators who extend from the leave exec node in the source code. These are typically scans that read from disk or from memory or reuse results from other queries. And then this is followed by one or more binary or unary transformations, such as the union in this example on the left is a binary transformation, which extends from the binary exec node. And for example, the columnar to row is a unary transformation extending from the unary exec node. So sometimes you'll see a specific operator dedicated to writing the output. It will not always be visible, but actually in the code, there's no difference. There's no specific write output exec node. It's all just a unary exec node. So actually, if you go through the source, there are over 150 subclasses of this physical plan. Again, like just to give you an overview, to kind of get an idea of how many operators exist in each of the categories. Actually, the biggest category is the unary exec node, which contains all transformations that work on one data frame as an input and produce one data frame as an output. There are only very few operators that work with multiple data frames as input, such as joins and unions, etc. And there's also quite some operators dedicated to actually reading data from either cache or files or from RDDs or other queries. So because there are so many different kind of subclasses, we of course cannot cover everything here. So basically what we will cover is the most common narrow transformations, most common wide transformations, such as aggregates and joins, and we will discuss how exchange operators and sort operators get into the query plan, because sometimes you simply will not get that one-to-one mapping from the data frame transformations that you wrote. So we will not cover advanced topics like adaptive query execution, streaming specifics, or other things that are more specific for this introductory talk. So let's just start with the very basics. Let's look at what happens if we just do a read from a data source and write to the data source. So on the left, you see that we read from a CSV data source, which is a row-based data source, and then we write out to a Delta Lake table. So this data frame transformations on the left actually translate to two queries on the right. The first query, query 1, denoted by Q1, is containing one operator called the save into data source command. This in itself doesn't start any jobs. Instead, it will actually just wait for the second query that it will spawn to be completed. So query 2 at Q2 actually is responsible for actually reading the data from the CSV file and writing it out to the Delta format. So as you can see as well on the right at the scan CSV operator, there are quite a lot of metrics here. and you can actually use these metrics to detect potential performance issues in your setup. So if we look at these metrics, I put numbers here, 1, 2, 3, 4. Actually, just starting with number 1, the number of files read, that's actually a very important metric to take into account. This denotes how many files were read as it says. It's like pretty simple. But if you combine this with the other metrics, such as 2, file system read, so the actual data that was processed going through this operator, and 3, the total size of the files that might still be processed. So you see that number 2 is actually much less than number 3 here, but it's expected to grow from 3 GB to 120 GB when this job is progressing. I actually took the screenshot when the job just started. So if we compare number 2 and 3 with number 1, so actually if you compare, relatively speaking, the number of files read with the size of the files read, you actually do not want to be in a scenario where the number of files read is a super big number and the size of files read is a super small number, because then you might be suffering from the small files problem, as has been talked about in many other performance talks. So then actually the Spark job might spend more time on discovering files rather than processing data. The fourth metric that is worth to highlight is the rows output. So this is also interesting to sometimes check if you're doing a query that's very selective. So you only want to get certain values using a filter, for example. Do you actually see this reflected here, or does it still output a lot of rows when scanning the data source, which might actually show you that the filtering predicate is not pushed down to the data source, and hence you might need to change something in your query there to optimize it. So here there's another example of just reading and writing, but instead of reading a row-based data format, we read a columnar format. So in this case, we read from Delta Lake and we write to Delta Lake. And people who might be more familiar with the internals of Delta Lake know that the Parquet file format is used to store the actual data inside the Delta Lake table. Hence, on the right, we see query 2 start with the scan Parquet operator. But then we see something new. So we do not just see the scan Parquet, but we also see 2 new boxes, namely the whole stage cogen and the columnar to row operator. So just to highlight, what is this? So starting with the columnar to row, this operator, you will actually see in Spark 3 whenever a columnar data format is read from. This is an operator that will actually convert the columnar format provided by Parquet in this case to a row-based format that is used internally by Spark to do all the operations on. Another box that you see here is the whole stage cogen on the right. So this box you will see a lot in different queries. This essentially just means that all the operators that are inside this box support whole stage code generation, which means in essence that they operate on an optimized data format and also use Java bytecode generation to execute the operations they actually perform. So it's both more memory efficient and more performant in terms of execution time. So you actually want to see these whole stage cogen boxes everywhere, because that means you're probably having the most performant implementation. So just zooming in on it's still the same query on the scan Parquet. There's lots of different statistics here. Some have to do specifically with the Delta IO cache that's available in Databricks. Other metrics are similar to the ones that we discussed on the CSV scan operator. one to highlight here is actually the scan time total at number 1. This shows you how long it takes to actually scan the data from the data source. This kind of metric is only specified for columnar formats and not in row-based data formats, because it's too heavy or too inefficient to keep track of this row-based timings. So here you can again see, like, if this is much higher than you expected, then you might have like some network connectivity or like slowness there. And by the way, this metric, it says 6 hours, but it's like consecutive time spent by all tasks on the entire cluster. So it's like the sum of time spent as if you would use just a single core to process everything. So then still same query, but now looking at the whole states code gen and column to row, I actually just want to highlight number 1 here. The others are kind of self-explanatory. So number 1 actually shows the duration here of the whole states code gen. This will be your main indicator of where to look in a query plan to find performance bottlenecks. So in this case, it says 52 hours. So it's really just the sum of time spent across all tasks in the cluster. So you always want to look at this metric, relatively speaking, to other whole states code gen blocks in the same query, and then just look at the highest duration. So it doesn't really matter if it says hours or minutes, just find the highest one, and then you probably have your performance bottleneck. And then you can look at the operators inside the whole states code gen box to see if there's anything you can optimize. So this actually brings us to the common narrow transformations. So we'll extend the example by just adding some simple transformations. So narrow transformations, recall that that's actually transformations on data frames that do not require a redistribution of the data across the cluster. So it can be applied locally on where the data resides at that point in time. So prime examples of them are filter, which is quite simple, just shows as a filter operator in the query plan. And another one that you see often is the with column or select statement. If you execute that, it will actually show up as a project operator. And if you hover over this project operator, this black box will show you the details of what columns are selected and modified in this case. So just to give some more examples, this is basically like super straightforward. Like if you do a range, you get a range. If you do a sample, you get a sample, union, etc. So it's pretty straightforward. These also do not give you much more information apart from the rows that they output, like the number of rows that they output. But here there's a bit more interesting case actually. So sorting, what if you want to sort your data? And remember, your data frame is just a distributed data set that's distributed over the cluster. So it depends what you actually want to sort. Do you want to globally sort it or do you want to locally sort it? So sometimes it's fine to just locally sort it. So if you, for example, do this sort within partitions transformation on your data frame, and here we do this on item ID, then the only operator that you will find is, if you look at the center here, is the sort operator. And it's part of this whole states code gen box. It doesn't require any redistribution of the data. So it will just sort the data as how it's distributed over the cluster and just sort the data in the partitions that you already have. So on the right, if you look at this table, you can basically see, going from the left to the right, what happens to the data after certain operations are applied. So in the first column, we have an example data set. For example, we have some partition X in the data set that contains item ID 33. Then another partition Y, which contains some other values of item ID like 34, 4, 8, etc. So then actually, if we apply the sort operator, the result will be as shown in the red column in the middle. So actually, there will be a local sort where within each partition, the values will be sorted. And then if you look at from a global perspective, you can actually see that it's not a total ordering. It's not globally sorted, the data set, because value 33 from partition X actually is before 4 and 8 of partition Y. So let's see what happens if we actually want to have a global sorting or ordering. These can be interchangeable. So let's say we do an order by on your data frame, then actually, semantically speaking, it assumes that you want to have a global ordering of all the data in your data frame. So now suddenly what happens if you look at the query plan at the center is that before the sort all the way at the bottom, there's this exchange that gets added into the query plan. So why is this? Well, in the local sorting example, we have seen that the result of just doing a local sort will not give you a global sorting result. Hence, we need to redistribute the data over the cluster to make sure that this global sorting is guaranteed. So again, we can look at an example here. So if you look on the table on the right, we have the same example, but now we have added an additional operator, the exchange operator, that's all in yellow. If you look here, after doing this exchange, which is basically shuffling the data over the cluster, redistributing across to a certain partitioning scheme, we see that the new partition X will actually contain the values 8 and 4, and then the new partitioning Y will contain the other values, including value 33, which used to be in partition X. If you then sort the data after doing this shuffle, you will actually end up with the result in the red column. And if you just assume that there's no partitions and look at it from a global perspective, you can see in the most right column that actually value 33 is now in the correct place and the data frame is sorted from a global perspective. So this actually was an example of wide transformations. So wide transformations are actually transformations that require a redistribution of the data or potentially redistribution of the data over the cluster. So examples of these are actually global sorting, like I showed you, but also joins and aggregations. And we actually want to see how does the query planner know that it has to put in these exchanges? Well, actually it does this through distribution requirements that operators can specify. So here, like this, again, a bit to theory and a bit looking at the code. So every Spark plan operator, so every operator in the physical plan can actually specify a required child distribution. And this is basically a requirement on how the data should be distributed over the cluster before this operator can be applied on the data. And then after doing this operation, it can also guarantee a certain output partitioning, which in turn then can be used for downstream operators to check if their required child distribution is met. So on the right, again, a table to look at what kind of required distributions are there, how are they satisfied, and then some example operators. I want to highlight two of them here. So the first one is an order distribution requirement. And this is actually the requirement for a global sort that we have seen. And This will actually be satisfied if the data is range partitioned, which means that if you partition the data, so if you distribute the data over the cluster according to a certain key, it actually needs to be the case that values of the key that are close together, like for example, values 1 till 10 or values 10 till 20, they need to be on the same node in the same task on the same machine in order to be able to do this sort operation in this case. Another example of this is the hash cluster distribution, which actually is satisfied by hash partitioning. So an example operator here is actually the hash aggregate, which we will discuss later, as well as the sort merge join. So what this distribution requires is that it doesn't have to have values that are close together in terms of a range, like values 1 to 10. They don't have to go to the same machine necessarily, but every value needs to go to the consistently go to the same machine. So if you have a key of value 10, it always needs to go to the same partition, and 9 also needs to go to the same partition, but it doesn't necessarily have to go to the same partition as the value 10. So just to make this a bit more concrete, let's go back to the sort operator. So if you want to do a local sort, you actually do not have a required child distribution, and thus when the ensure requirements rule is applied, it will not add an exchange because it's not required to have a certain distribution for this local sort. But actually, if you want a global sort, then the required distribution will be an ordered distribution. And if the ensure requirements is applied in this case, it will actually inject an exchange operator with range partitioning before the sort. And then the sort will actually guarantee the range partitioning as output, so that if you have multiple sorts in a row, it might actually not have to again shuffle the data, but can already know that the data is distributed in a certain way to meet the requirements. All right, so let's look at some details of the exchange. So there are actually two kinds of exchanges, the shuffle exchange and the broadcast exchange. So the shuffle exchange here shows on this slide. So what does a shuffle exchange do? Basically, a shuffle exchange always consists of two consecutive stages, as seen here in the exchange operator visualization on the right. You see stages 4 and 5. So one stage will actually write out shuffle files to disk, and then the second stage will read those shuffle files in according to the required distribution of the operation that requires the shuffle. So two things to note here. One is if you look at the metrics, there's a size of shuffle bytes written all the way at the bottom, and then there are two other metrics that should correspond to, like the sum of those metrics should correspond to the total shuffle bytes written. So in this case, there's a local and a remote size of data read. These data sizes are actually important to take into account if you see a very big number here and you only have certain number of shuffle partitions configured for either the stage that's writing or reading, then you might actually start spilling to disk because it might not have a lot of memory or enough memory to deal with so much data per partition. So this is something to keep in mind here. Another implementation is the broadcast exchange. This is a typical exchange that's implemented for data sets that are small enough to be broadcasted, so they don't need to be spilled to disk. They will actually be collected on the driver and then being broadcast to all the executors. And the most commonly used operators that use this are the broadcast hash join and the broadcast nested loop join that Max will also tell you more about. So before I let Max speak again, I first want to actually zoom in on the aggregate operators here, which are example of wide transformations. So here on the left, you see we do this group by aggregate on a data frame. So we aggregate, we want to have the sum of all sales per item ID in this case. So in the center, you see the actual physical plan that's shown in the Spark UI. So you'll notice at the bottom that there's this hash aggregate operator, which typically comes when you do this group by aggregate. And then because this hash aggregate has a distribution requirement, this exchange is added at the top. So it actually has a distribution requirement that all the item IDs that are equal should end up to the same machine so that they can actually be added up with all the sales. So on the right, you see this example where we have, again, a data set, but now I just added item ID and sales. So in the first column, you see that we have actually an item ID A and an item ID B, and we have different sales values per item ID, and they're also spread out over different partitions. So A and B are both present on different partitions, which might be on different machines in the cluster. So first, in order to get all the values of the identical item IDs to the same machine, we do this exchange, and the result shows in the center column with the red colors. So we see that all the values for A will be brought to a new partition X, and all the values for B will be added to new partition Y. And then finally, we can actually do this hash aggregate, which will actually, in this case, because we do a sum, will sum all the different values to get the final result that's shown in the green column here. It's called a hash aggregate in this case because hash table data structure is used to actually store these results, where in this case, item ID will be the key and the values will be the sales numbers. So apart from hash aggregate, there are other kind of implementations when doing an aggregation. So actually the default, and you will almost always see this one, is the hash aggregate that we showed on the previous slide. As I said, it's based on the hash table structure, and it supports code generation. This works for most cases. Even when your cluster doesn't have enough memory, you might still be able to use this hash aggregate, because if it will simply build the first hash table, and when it runs out of memory, it will flush that to disk, start a new hash table, and then finally merge all the results using sort-based aggregation. Then actually in the occasions that the hash aggregate cannot be used. So one example of that is if you do a collect list instead of a sum, you're actually collecting data in a buffer that has variable size. So in this example here, we're just adding a counter for sales. So we just adding up a number, and we can just use a fixed size for that. We can use, for example, a 64-bit integer value there. And hence we can use this hash aggregate implementation. But for some operations, this is not possible. So if we do, for example, collect list, we might actually keep accumulating more numbers in an array. And this is not a fixed size. And then it will actually fall back to this object hash aggregate, which works similarly as the hash aggregate, but has some other intricate details, such as supporting operations of non-fixed size, but also supporting aggregations for the dataset API that are on custom Java-based objects. So if all is lost, and this is actually in very rare occasions nowadays, because most of the hash aggregate and object hash aggregate are supporting most of the aggregations, then it will fall back to a sort aggregate, which does sort-based aggregation. So that's actually having a bigger time complexity. So instead of just accumulating values in a hash map and having constant lookup to add the new values, it will actually first have to sort all the rows and then do a single pass to collect all the results, which is slower because sorting has a higher time complexity than just looking up values in a hash table. The only metric you want to look at in hash aggregate typically is the spill size. Actually, you always want this to be 0. If this is higher than 0, that means that it has started a fallback, as I explained before, where it tries to first do the aggregation with one hash table in memory, but then it runs out of memory. Then it has to flush this to disk and start a new one, which will obviously add more overhead of merging the resulting hash tables, reading and writing from disk, etc. So if you run in this situation, you typically want to look at, are my data set sizes per partition too big, or do I have too little memory per core in my cluster? Then one note on partial aggregation. So I just showed the example of first doing an exchange and then a hash aggregate to show like how aggregation works in this root setting. But as Max pointed out way in the beginning of this talk, typically you'll see this double pass hash aggregate. So you first see a hash aggregate, then an exchange, and then a hash aggregate. So in this example, we just want to show what that is. It's actually partial aggregation. So the example is exactly the same as how I showed, but now we have this yellow column in the table again. So what it does before exchanging the data of the cluster, it will attempt to actually already partially aggregate the results before sending this over. So in this case, for partition Y, you see that there are multiple rows that have the key B. So there's like 3 rows of them. So what this partial aggregation operator does, it will simply consolidate all these into one row, in this case B with sales value 4, before actually doing the exchange. So this will actually reduce the number of data points that are shuffled over the network, which might in turn improve the performance of your job. The remaining operations are identical. So I think I talked enough for now. So I actually want to give the floor back to Max, who is going to talk a bit more about joins.
Cool. So yeah, joins are the last white transformations we are going to cover. So in this slide, there's a typical example of a join, right? So on the left, we can see a typical join query in which we join a sales sample data frame to some item dimension table on the item ID key. And this will then be an inner join. And on the right, we then see the associated query plan. So first of all, we see the actual join operator on the bottom right, which in this case is a sort merge join operator. But what is really interesting is that there are a lot of things actually happening before we even arrive at the join operator, right? So first of all, we see 2 sorts. So both of these data frames are being sorted. And then even before that, there are also 2 shuffle exchanges before both the data frames are being sorted. And even before that, also the 2 data frames are actually being filtered. So this entire query plan is generated just by doing this join operator. So what we now really want to know is, first of all, we are now seeing the sort merge join, but what join algorithms actually exist, right, within Spark? And second of all, we also want to know, how does Spark actually choose what join algorithm to use? So on the basis of what kind of rules does Spark, for example, choose a broadcast hash join, broadcast nested loop join, or this sort merge join. And also, lastly, as I already just said, where are, for example, the sorts and the filters coming from? Stefan already, of course, explained a bit about the child distribution. So this kind of means that, well, we can already kind of guess, right, that the sort merge join operator probably has these child distribution requirements, which leads to these two shuffle exchanges. And we will then find out in the next few slides that similar type of requirements actually also lead to these two sorts that are happening before this sort merge join operator is actually executed. So what kind of join implementations do we have? So in this slide, you will see a table of the 4 most common join operators and what their required child distributions are, the required child ordering, a brief description of what all these operators do, and a ballpark complexity estimate. So the quickest join implementation is actually the broadcast hash join. Logically, of course, and it's of course logical that for the required child distribution, one side actually has to be broadcasted. So one of the 2 data frames that's going to be joined should actually be small enough that it can be broadcasted to all the executor cores. There's no required child ordering because the data frames do not actually have to be sorted before doing this join. So what does this join actually do? It just performs a local hash join between the broadcasted data frame in its entirety and that particular partition of the left data frame in that particular executor core. Because there's no sorting or anything like that going on, it's just a local comparison between the broadcasted data frame and the partition. The complexity is only O(n), right? So the other the other very common join operator is the sort merge join that we just saw in the past example. And for here, we actually have a required child distribution to be a hash clustered distribution, which is the same required distribution as you saw for a typical aggregation query. And this essentially just means that the data frame has to be hash partitioned, which means that all the keys with the same value have to be on the same partition before the join can actually be executed. Next, the sort merge join exec also has a required child ordering. It requires both of the data frames that are going to be joined to be sorted before it can actually be executed by the join. Once this is done, the only thing the sort merge join operator actually does is it really just compares the keys of all the sorted data frames, and it just merges those keys if there's a match. The complexity of the sort merge join exec actually fully comes from this required sorting, right? As sorting a data frame is typically O(n) log n, so that is really the complexity of the sort merge join exec. The actual joining itself is only O(n) complexity, so again, all the complexity comes from the sorting. The other 2 join operators are significantly more complex. So the first one is the broadcast nested loop join exec. Again, this requires one of the data frames to be broadcasted. Well, for the other data frame, there's no distribution requirement. There's also, again, no sorting requirements. So what does actually happen in a broadcast nested loop join? So this is actually kind of similar to a broadcast hash join, but instead of performing a local hash join, it actually operates in a loop. So for each row of the left data frame, which is basically the partition, it will actually compare that row with the entire broadcasted data frame and see if any keys are matched, and if yes, it will merge those. So for each row, it will loop over the entire broadcasted data frame. And this basically means that the complexity then becomes O(n) times n, where n is the size of the left data frame and m is the size of the broadcasted data frame. So the last join operator is the actual Cartesian product exec. And what happens in this one, it's essentially doing a cross join between the 2 data frames it tries to join. And afterwards, it will then do a filter on to only retrieve the rows that actually match the join condition. So what do I mean with a cross join? It basically generates all the possible combinations of rows between the left and the right data frame. This is also quite high complexity, again, O(n) times m. Compared to a broadcast nested loop join exec, the m typically tends to be a bit bigger. So this operation tends to be more expensive again compared to the broadcast nested loop join exec. So how does Spark actually choose its join? So on this slide, you see a flow diagram of how Spark ends up choosing a join implementation. So the first choice Spark has to make is the first thing that Spark actually looks at is whether a join is an equi-join or not. So is there an equality statement in the join statement or not? So for example, does item ID have to be equal between two data frames, or should it only look at the range of item IDs? So if it's an equi-join, then it will look at whether one of the data frames is small enough to be broadcasted, given some threshold configuration that's in the Spark code. If the broadcasted data frame is small enough, it will then choose this broadcast hash join, which is the quickest possible join. If if both the data frames are not small enough to be broadcasted, it will actually choose a sort merge join. If the join is not an equality join, so there's not an equality statement within the join condition, then it cannot do a sort merge join or broadcast hash join. It will actually have to do a broadcast nested loop join or Cartesian product, which you can see on the bottom of the flowing diagram. So again, it will first look at whether one of the data frames is small enough to be broadcasted. If it is, it will then execute a broadcast nested loop join. If not, it will then have to resort to Cartesian product. But this is actually only possible when doing an inner join, not when doing like a left join or a full outer join. So if it's then, for example, left outer join, Spark will then try to do a broadcast nested loop join anyway. But given that both of the data frames are not small enough to be broadcasted, this will actually then lead to out of memory errors. So this can be very dangerous. And basically the key takeaway of this is that you really should try to avoid doing any kind of non-equi join, which is a left join or a full outer join. So lastly, I briefly want to touch upon ordering requirements. I already covered this for a bit, but so next to the distribution requirements that Stefan mentioned, some operators also have an ordering requirement, most notably sort merge join. So the sort merge join requires the two data frames it's going to join to both be sorted on their join keys. So on the left, you can see, for example, that the data frames are going to be joined on left.id and right.id. And sort merge join exec operator then basically says, well, I require these data frames to then be ordered on the left ID and right ID respectively. And this then means that the Spark plan will actually generate two sort operators on top of the sort merge join to meet this sorting requirements. So as you can see on the right, there are now then two sort operators, both for each data frames, that then make sure that the data frames are ordered on their join key. So let's just revisit our join example, right? So given all the information I just talked about, we can now analyze a bit better what is actually going on in join. So first of all, it does a filter, right? So it actually turns out that in a step even before the physical plan, but in a step called the logical plan of the catalyst optimizer, Spark is able to figure out that because it's an inner join, it can already move all the join keys that have a null value. So we'll actually add a filter on is not null for you in the query plan. Next, we know that the sort merge join has required distribution of a hash partitioning, and this causes Spark to add in a shuffle exchange for each of the data frames that are going to be joined. Lastly, there's then also the required chart ordering, because the sort merge join actually requires both of the data frames to be sorted. So this causes two sorts to be added before the sort merge join operator. Finally, Spark has seen that, well, this join is actually an equi-join because it contains the equality statement on the item ID. And it has also determined that both of these data frames are not small enough to be broadcasted, and as such has ended up with the sort merge join. So this really should give you now all the information you need to see what is going on when looking at the join, when looking at the query plan of a join. So the last section of this presentation, I quickly want to go over a couple of real-world scenarios of Spark queries that can be optimized by looking at the query plan. So in the first example, we have a data frame that contains a category column. For example, a product category of a supermarket. And what is a typical use case is that for each category, you want to apply, say, a different product discount. So one way to actually solve this is that you union 4 data frames. And for each of these data frames, you filter on a specific category and then apply this discount function. And for each category value, we'll then have a different discount function. But if you then create the query like this, what Spark will actually end up doing is it will read the Parquet files 4 times, as you can see on the right. And because these are repeated reads of data, this is really typically a suboptimal query. So by looking at this query plan, this is something we've now found out. And the next question is then, can we somehow rewrite this query to optimize it so that it only reads the data once? Well, and so it turns out we can. So instead of doing a union and then with 4 filters, we can actually just apply a case when statement, right? So for each of these product categories, we can say, well, when the category value is this particular value, apply this function. When it's another value, apply that function, and so on and so on. So you can create this chain of case when statements. And by doing it this way, we can actually write a query that the data frame is only read once, as we can see on the right. So it's not only one read. And this essentially means that the Spark query is much quicker compared to the last query in which we did 4 reads. So the second scenario I want to cover is partial aggregations. So as Stefan already explained, in most aggregation queries, there's actually partial aggregation done to basically reduce the amount of data that has to be shuffled around before doing the final aggregation. However, this actually turns out not to be always very helpful. What, for example, if you have a grouping key that has a very high cardinality or has a lot of distinct values? So in this particular data frame, of which we show an example on the left, the number of distinct item IDs on which we want to group is almost the same as the number of total rows in the first place. But this then actually means that doing a partial aggregation is really not going to help a lot with reducing the number of rows that are going to be shuffled. And it's in fact actually only going to increase the query duration. So in this first example, in which we still have enabled partial aggregations, we see that the query duration is 23 seconds. However, if we now actually turn off partial aggregations, and this can actually be done by turning on the configuration, as is denoted on the left side of the slide, we are actually able to remove this partial aggregation step in the query plan. And in this particular case, it actually leads to a speed up of the query of almost 22%. And we brought the query duration down to 18 seconds. I just do want to note that partial aggregations, right, tend to be really good because, well, in a normal use case, they really do reduce the amount of data that has to be shuffled before the final aggregation. But again, there can be these specific examples, like for example, this one, where, well, it actually benefits from being turned off. So the final example I want to show you concerns join strategy. So in this example, we have a data frame with ships and all their respective longitude and latitude coordinates. And we also have another data frame that contains ports, which have a bounding box of coordinates. And what we actually want to figure out in this example is whether a given ship is within a port or is at open sea. So what is one way to figure this out? Well, we can then, of course, do a join. And what we do in this join, as you can see on the left, is we actually want to see whether the latitude coordinate of a ship is within the min and max value of a port latitude coordinate. And we want to see whether the longitude coordinate of a ship is within the min and max longitude coordinate of the port. But this actually leads to a non-equality join, as you can see on the left. And as you may recall from our join strategies flow diagram, this means that Spark will try to choose a broadcast nested loop join. So luckily, it turns out that DF ports is small enough to be broadcasted, so it does not have to do a Cartesian product join. Nonetheless, a broadcast nested loop join is actually still quite slow. And as a result, this query takes 3.5 minutes. So the question is then, can we do something about it so that Spark actually chooses a different join strategy? So, and it turns out we can, right? So one way to solve this, because we're talking about coordinates, is basically by defining geohashes, which are basically large rectangular areas that define these coordinate boxes. And in order to figure out whether a ship is near a port, we can already say, well, that probably then means that the geohash of the ship and the port is the same, before even looking at whether the ship is in the port or not. So what we now do to the data frame query, to the join query on the left, is we actually add a equality statement on which we say, well, the geohash of the ship should be the same as the geohash of a port. And by doing this, we actually ensure now that the join is an equality join. And this means, again, recalling the flow diagram of joins, that Spark can now actually choose a broadcast hash join or a sort merge join. In this case, the if port is small enough to be broadcasted, so Spark will actually opt for a broadcast hash join, which is the quickest join implementation there is. And as we can see, the query duration time has actually drastically been reduced from 3.5 minutes to a mere 6 seconds. So this is really an example of, by changing the join strategy, we really accomplish a drastic reduction in time. Yeah, so having discussed these three scenarios, this kind of brings us to the end of the presentation. I just quickly want to go over what we actually discussed in this presentation. So we have seen in beginning and through the explanations of Stefan that the SQL tab provides a lot of insights into how the Spark query is executed, right? So it really gives you a breakdown of all the operators that Spark is using to execute this query. And so we can use the SQL tab to reason about the query execution time, especially by looking at the total duration of each of the whole stage code gen blocks that Stefan explained. And by using these insights, we can answer important questions like, what part of my Spark query takes the most time? And is my Spark query actually choosing the most efficient Spark operators for the task? And so as we saw in the last part of this presentation, we can then actually analyze this query plan and sometimes see, well, no, it's actually not choosing the most effective query plan. And then you can rewrite your Spark query, your Spark query in such a way that a more optimal query plan is actually chosen. And this can really lead to large reductions in your query time. So if you want to practice or know more, there are a couple of tips we can give you, right? So what we typically suggest you to do is that whenever you write a Spark query or a data frame query, is to really mentally visualize what the physical plan would look like without actually looking at the SQL plan. And then to actually look at the SQL query plan and compare whether you were actually correct. And if you are not, try to reason about why that is. The next what we would suggest you to do is to actually go into the Spark source code and look up the Spark plan class, because this is really this class that contains all the methods and all the operators. And from there, you can really dive into deeper into the Spark code to really see how the Catalyst optimizer computes this query plan, and you will be able to learn a lot more from there. So this is the end of the presentation. Thank you very much for attending.